My name is Brian Bach, and this is my ENME 489Y final presentation video. Remote sensing is the measurement of objects from afar, without direct physical contact. As a field, remote sensing has tons of very interesting applications. In this class, we focused on range measurements used to determine geometry, size, and position of objects at a distance. We were tasked to pick an object on campus and map it using computer vision-based LiDAR. For my target, I chose the Frederick Douglass statue on Hornbeck Plaza. The statue has a lot of complex, interesting geometry that would be difficult to parameterize with conventional means. I also thought this geometry would lend itself well to recognition even at low resolution. Here are some fun facts about the statue, the most important of which are the first two, which I'll talk about more later. The sensor apparatus consists of three major components. There's the line laser, which acts as a transmitter, and the Pi camera, which acts as a receiver. The Raspberry Pi interfaces these components and acts as the central processing unit. Importantly, the line laser and Pi camera are rigidly mounted 305 mm apart. Both the Pi camera and Raspberry Pi are secured via tiny zip ties. This sensor is an active sensor. Active sensors have their own transmitter and light source that they use for sensing, whereas passive sensors use ambient light. I started out using a green point laser. Calibration of this setup involved taking photos at discrete 6-inch intervals from a wall, from a range of 10 feet to 0 feet, and then evaluating the data. With some minor adjustments to the compensator values, the data closely aligns with the idealized values. In order to get the laser, and only the laser, to show up clearly in the photos, I had to fiddle with the HSV values for each trial. Calibration of the line laser was a very similar process. Involved moving the laser at discrete 6-inch intervals from 10 feet away from the wall all the way immediately up to the wall, and noting how the line laser moved in the field of view. As the distance from the wall decreases, the apparent position of the line shifts. It is this shift that we use to calculate distances. Just like with the point laser, we find the data from the line laser test aligns pretty well with the idealized values, shown in blue. I wanted to incorporate a servo into this design to enable automated scanning, with the idea being that if I got this working, I could just press go, the system would run, and I could come back a few minutes later, and the data collection process would be complete. I modified the chassis to incorporate a servo horn, and included a tripod servo adapter that I had previously made for another project. Unfortunately, this approach was rife with issues. Connecting the servo to an external power supply made no difference. It seems that the clock used to regulate PWM signals for servo control is also needed to take a raspistill photo, making them mutually exclusive and totally incompatible. The fall you saw a moment ago damaged the chassis and knocked the laser off. When I reattached the laser, it was misaligned, which caused an issue for my first trial of scans. The laser line in this photo is supposed to be vertical when aligned. I had to manually realign the laser and then secure it in place with copious hot glue.
The servo is very jittery. What I'm doing is I've been holding it in each position with my hand. Also, the servo horn is not actually screwed into the servo, so there's a tendency to fall out and have the chassis fall to the ground, which is obviously not a desired outcome. Like that.
As any photographer could tell you, a long exposure plus a shaky camera ruins a photo. I had to throw away most of the data collected in this first trial of scans, as many of the photos taken were way too blurry to be useful. After fighting with the servo and its issues for some time, I returned to the original fixed chassis design, which mounts rigidly to the tripod via a different adapter. I used my phone zip-tied to the mount to record the angle of the system. Now that I finally had a fully functioning, easy-to-use sensor, I was ready to go out and scan my target. I did 6 scans of the Frederick Douglass statue, with each scan roughly spread equidistant about the circumference around the base of the statue. The dark, low reflectivity of the statue required that I do a 1 to 2 second exposure per photo to fully capture the laser line. This also required that I be very close to the statue, otherwise the laser wouldn't show up, which made it difficult to fully capture details towards the top of the statue, as I was pointing up instead of at those features. This is the code used to take each 1 to 2 second exposure of the photos used for the scans. For each scan of the statue, I slowly worked my way up, angling the tripod at roughly 3-degree increments. From some sides of the statue, the square pedestal was reflective enough to catch the laser line being shown on the circular base below, which messed up the data collection there. So for some sides, I started closer to the base of the actual statue, the rocks that Frederick Douglass is standing upon. I tried to move in as small increments as possible in order to capture the most detail to aid in the point cloud combination later. Frederick Douglass's cape, with its complex wavy geometry, was the most difficult feature of the statue to capture. The data was then processed in Python using the following code. These scripts created a series of TXT files with the XYZ coordinates of each point. I did 6 scans of the Frederick Douglass statue outside Hornbeck. Together, they produced the following 6 point clouds. These points are probably noise, but the legs are clearly visible here. Again, the legs and statue base are easy to see in this scan. There is an extraneous data point somewhere over here that will need to be filtered out for data processing. The process of aligning these point clouds was extraordinarily laborious. It involved carefully and often repetitiously comparing and making minor modifications to the transforms, recomparing and making additional transforms. To make matters more difficult, the origin and the z-axis that these rotations are done about, it does not occur in the visual center of the point cloud, but rather some distance further away. Due to this, each rotation transformation had to be followed up with additional fine-tuned translation transformations, adding to the tedium and difficulty of this analysis. I started by comparing the first scan with the second scan, the 2 scans which should have been closest in similarity. Once I aligned the second scan with the first scan fixed in place, I moved on to the second scan, comparing the second scan and the third scan. This process repeated, so on, with each successive scan as I worked my way around the statue. On average, it took about 15 to 20 minutes to align each point cloud cluster. In this video, the magenta point cloud is the original one, or the previous scan, and the green one is the one that I am adjusting. This point cloud is the nearly perfectly matched results of the first and second scans. Due to the point cloud density, these 2 scans were the easiest to compare and merge. Other scans were more difficult due to their more sparse nature. This shows the second and third scans, which mesh together pretty well. As I scanned, I moved around the statue, counterclockwise. I found the regions on the back of the statue, with the cape, which was poorly captured, to be much more difficult to align than the easily recognizable front of the statue with the legs. When I finished combining the point clouds, I exported them into one and began viewing them in MeshLab. There are a couple recognizable features in this point cloud that are worth noting. The outstretched arm of Frederick Douglass. The statue's legs are one of the more easily recognizable features. The cape billowing in the back. The statue's pedestal and the circular platform that it's on. I made several attempts to mesh this point cloud and turn it into a solid 3D mesh. None of them were successful. This last attempt is probably the best this mesh is going to get. Upon looking closely, it is possible to see and recognize the pedestal of the statue as well as its 2 legs, but the rest of this mesh is pretty much useless. This semester I also experimented with photogrammetry. Photogrammetry is an alternative technique for creating point clouds that uses many images and computational power to compute a point cloud from the images instead of from direct range measurements. I took 161 photos and let my computer churn on the data for nearly 8 hours of full CPU and RAM utilization. The resulting point cloud, though, is significantly more impressive than the one created with my LiDAR chassis. Each point in the point cloud maintains the colors of the photos it was taken from, which makes the statue even more realistic than just a regular point cloud. This point cloud is comprised of nearly 5 million points. I attempted to mesh this cloud, but the process ultimately failed.